To address this question of what about alpha, last time we gave the following argument. We assumed something called Parsevals theorem, which says if I integrate up the product of psi star, some general function, times some other general function, phi, and I integrate them up, I will get exactly the same answer as though I were to take their corresponding Fourier transforms and to take the corresponding product and integrate those over all possible wave vectors k. Now that's more general than we need to address this question of the value of alpha, but as we'll see later in the lecture, it's an extremely handy fact that we can use to also address averages in quantum mechanics. Now, I'm going to introduce a little bit of notation here along the way we didn't have last time, which was whenever I have an integral like this, right? There's a shorthand notation for it. This is the rest of the so-called bra-ket notation. We had seen the ket before. When we put the bra piece, the psi, acting on the ket, this bra-ket, what it really means is this particular type of an integral. I take all the values of psi at all the points in x, I multiply them by all the values of phi at all the points in x, and then I add them up. So this is a lot like a dot product, or sometimes what is called an inner product. Because there is the star here, there's a special name for these. These are called the Hermitian inner product when it has that complex conjugation. So that's really what we're dealing with. And then I'm saying that, well, that integral was the same as this integral, where again, what the bracket means is I star the first function, I multiply by the second function, and then to form the bracket, I integrate over the relevant variable. Now, if this theorem holds, then we have the following very nice chain of logic. We know that 1 must equal the integral of the probability of finding the particle somewhere. But that probability for finding the particle somewhere we know is just the magnitude of psi squared. Now, as we're learning, although this may be a nice compact notation and way to think about the magnitude of psi squared, for any types of formal manipulation, you're almost always better off as writing that as psi star psi. So integral of the probability is really the integral of psi star times psi, and then we can see this is perfectly in our form for Parsevals theorem, where we just happen to choose the function phi to equal the function psi. So this is just the bracket of psi with itself. But now by Parsevals theorem, which holds true in general, this bracket must equal the same bracket but in the inverse transform, or in the momentum representation, which really means this integral over k of the psi tildes, psi star times psi. Next, we know that psi star times psi tilde star times psi tilde is magnitude of psi tilde squared, but the magnitude of that squared is actually the probability of observing value k, but then divided by alpha, because I have to solve for psi squared. So psi squared is p over alpha, or as I've written here, 1 over alpha times p. Alpha is my normalization constant factor, which from my proportionality, which I then can pull out of my integral. I have 1 over alpha times the integral over all possible momentum probabilities. Well, that's just the total probability that my momentum has some value, so that integral must give me 1. So this chain of logic tells me then that 1 over alpha must equal 1, so therefore alpha is 1. And that's beautiful. That would be great if alpha was 1, because then I don't have to worry about alpha anymore. So if I can prove Parsevals theorem, I can get rid of this proportionality constant. Also, I will just comment that if we are careful, when we think about any other type of an observable, to pick appropriate normalization factors, right? This fact that we're about to prove, actually, we will see, depends on my choice of how I split up these two pies. Now, my point is that if we, in general, for any observable, when we think about its more general superposition instead of the superposition for momentum, and always work hard to ensure we have something that corresponds to Parsevals theorem, then by exactly the same logic, we can get rid also of this proportionality constant, alpha prime. So that's something we will always implicitly assume we do when we build up some new representation for any other types of observables that might be out there. Very good. So what our real task before us today then is to actually prove Parsevals theorem.